Here we come to our last sections, and that is the applications of the analysis of the stress to what we call the pressure vessels. Pressure vessels is a very practical, I would say, have quite a few applications. For example, the propane tank you use, that is one kind of the cylindrical pressure vessels. And here we have two kinds. The first one is the thin-walled pressure vessels, the cylindrical type. And the first step is we want to derive the approximated equation for describing the distribution of the stress. So here we have two kinds of stress. One is the sigma 1 pointing into the loop direction or circumferential directions, and sigma 2 is in the longitudinal directions. And for all the pressure vessels, if we would select our coordinate system in such a case, pointing x in the longitudinal direction, then using your right-hand rule, define y and z. So in such a particularly chosen coordinate systems, and here we define the sigma 1, sigma 2, and that this particular orientation has been in the principal directions of such a pressure vessel. Okay, so again here we pick up the x, y, z like this one showing, and that has been the principal direction. So basically this kind of saves us a little bit kind of troublesome of doing unnecessary the operations or calculation for determining the principal stresses. So keep this in mind. So now let's first one take a look at how to find the approximate expression for the hoop stress sigma 1. So to do that one, we simply pick up the free body diagram. In that free body diagram, hopefully can expose the distribution of the sigma 1. So in this case, we pick kind of this shape. Okay, in this case, these sections, this cross-sectional area, there's a two strip that is exposed the cross-sectional area, and in which sigma 1 will be on. So that is a selection. So in this kind of z direction, we take the equilibrium. So on one side, on the two strip, that is the distribution of the stress. So that is this case. This case, sigma 1 is the stress, and 2 is meaning the two strip. T times delta x, that is the area of the strip, each strip. Okay, on the other side, let me use the color here, in this projected area, and in which the pressures, the pressure of the tank uniformly applied to, and that exposed to the counting or balance force to the internal stress. So that is this one explained to this one here. Okay, and this is the area of this highlight here. Okay, so for this case, we can quickly get a very approximated expression like this one here, and keep in mind what is r. Per our diagram here, r is the internal radius, the inner radius. To apply this equation correctly, keep this in mind. Keep this in mind. I say one more time, r is the inner radius. That is the last time I say so. And again, a lot of students made a mistake. They simply take r not by following this definition. Okay, one more time, r is the inner radius, and T is the thickness of the wall. Okay, so that is the wall thickness is T, and P is the gauge pressure or internal pressures and of the vessel. And this is a very approximate, roughly approximated solutions. And this solution is good enough as long as T is very small. How small? Usually we say T is much smaller than R. And this one basically means the 10 times smaller. Okay, so that means this situation gives us what we define as a thin wall. Okay, so people will ask, hey, what does the thin wall mean? You simply providing this one, that'll be good enough. If the thickness is too thick, violating this quantity requirement, then I can tell you this equation won't be good. Okay, so again, this is a very approximate, very kind of roughly approximate equation, but this such a approximation is good enough for thin wall vessels. Okay, let's move on. So the expression for sigma 2, hopefully we can take a verbal diagram and have the cross-section area exposing sigma 2. So that is this kind of this area. Let me highlight here. Okay, so on this kind of the ring area in which the sigma 2 times dA applied, then again the applications of the area in this area applied, that is where the pressures applied. Okay, so two portions, and this one is the pressure applied to the black color, and this one is is the application of the reaction of the stress to, and in the kind of the ring red area. So again, we get into balance, we have this one here. So again, this is a very rough, easy approximation, but this approximation can be good as long as that applied to thin wall. And here, that's a formula here, and probably you need to memorize, or this been provided on the cheat sheet. Okay. So for this case, we remember sigma 2 equal to PR over 2T, and sigma 1 equal to PR over T. And again, here is our vessel, and we pick a stress element. On the stress element, we pick, this is our x-axis, this is our y-axis, and the element of the stress is this sigma 1 and sigma 2. Okay, so keep this in mind. Then we can build out the Mohr circle for this case. The Mohr circle for the blue ones, average equal to sigma 1 plus sigma 2 divided by 2, and that is 1/2 PR over T plus PR over 2T. Okay, so that is and the radius equal to sigma 1 minus sigma 2 square plus tau xy square, because again that has been in principal stresses, so this equal to 0. So this is PR over 40. Okay, so from this case we can draw the Mohr circle, and that Mohr circle actually corresponding is this case. Okay, so for this case, let me build up the point. So in this plane, this is the x plane, so we have sigma 2 and 0, and this one is our y plane. We have the sigma 1 0, so sigma 1 is PR over T, and this one is PR over 2T. Okay, so here this is our label x, and this is our label y. Okay, so hopefully get clear about the drawing what we did here. So for this case, we have the stress element, something, let me redraw this one here. Okay, so this is our xy, and so PR over 2T and PR over T. Okay, so that is on the blue circle here. Then if we extend it into the three-dimensional view, then we can have the other two circles being plotted. For example, if you are the little guy sitting from here in front of you, what you see, this is the projection you're going to see. So project to you is PR over T and 0. So for this one, corresponding is this biggest circle here. Okay, so now we change the other viewpoint. So for example, if you look at these things from here, so this is the surface projecting to you, so that has the from here is let me double check. Oh, sorry, this one we have done. Never mind. Okay, but let me copy it. Let me do it. So in front of you, this is PR over 2T, and PR over 2T, and this one is PR over T. Okay, so that one basically is the circle. Let me change color. Okay, since I have done so, so let me just get everything repeated. Okay, then the third one will be let me use this color. So you are the little guy sitting on this axis looking downward. So in front of you, what you see is PR over 2T and 0. So basically that corresponding is this circle here. Okay, so basically again using the color code and corresponding to which circles we're dealing with. So from here the question is this: what is the maximum shear stress in the pressure vessel? And from here the answer can be very easily answered by looking at this graph, and the maximum circle is the red one. So here is the maximum shear stress. Okay, the maximum shear stress occurs in such the orientation. So that means that orientation will be, say, rotated about this axis by 45 degrees. Okay, by 45 degrees. Okay, and this one, this guy is sitting in this view. Basically this one corresponding is this element in this view. So this is our given we call the in-plane information. So that means here you can see this projected area basically aligned to the patch we select from the surface, or from a surface parallel to the thickness level of the pressure vessel. So this is called the in-plane in the given plane, okay, in the assigned viewpoint of the plane. And the other two directions we call the outer plane. So this viewpoint is called the outer plane. This is also called the outer plane. The maximum shear stress in the pressure vessels happen in one outer plane view. Okay, so keep this in mind. Then so here is kind of, if you have a printout, that's a detail the explanations, and then also you can read the textbook for the in-plane, outer plane concepts here. But basically that is what I explained here. Okay, so the second type of the pressure vessel is the spherical-like. And so here we simply pick arbitrarily the patch, square patch. Okay, so let me change color here. So the square patch from the surface. Okay, so then we simply we again taking the similar way. If you pick a cross section, exposing the cross section, the half sphere, and something like this one. So basically this area, this is the ring area in which the stress tube acting on. Okay, so and then the inner, the circular area is to which the pressure applied to. So under the simple equilibrium equations, you can find that sigma 2 should be equal to PR over 2T. And once you've done this, and you can repeat the selections of the cross section. For example, here you can pick another the free body diagram. Okay, So repeating the same thing to expose where the sigma 1 is, and you can find that sigma 1 will be equal to sigma 2 because this kind of the center, the isotropically symmetric features of the sphere. Okay, so for this case, this is our in-plane information. So in-plane information, let me do this one here. So this is our stress element. So let me do this one here. Okay. And then for the in-plane, let me designate this is xy. So this is PR over 2t. And this is PR over 2t. And one is sigma 1 and one is sigma 2 here. Okay, so here I simply define my xy like this one. So that's the in-plane. So this is the in-plane in the given plane, in the assigned plane. So now I want to extend it into 3D view. Okay, so in the 3D view, then again, let me change colors here. So for example, you are a little guy sitting here looking into that one. So basically projecting to you is the in-plane informations. So do I have a circle being drawn here? Okay, I have a circle being drawn here. So in front of you, this is the one here. So let me draw this one here. So in front of you, this is the sigma 1 to PR over 2t, PR over 2t, and this is our xy here. Okay, so basically here drawing is this point, actually corresponding to this one, Mohr circle. This is a shrink to 1 point. 1 point as a particular case of a circle, so corresponding to this one here. Then let me change the viewpoint. So for example, if we the little guy sitting here and looking into from this viewpoint, so let me highlight there. So in front of you will be PR over 2t, PR over 2t. So in that case, corresponding circle is this one. Okay, and then we change the viewpoint to this one. So again, if you are a little guy sitting here looking downward, so again in front of you, you can see is PR over 2t and PR over 2t. That's it. So basically the third one basically is identical to the previous blue one here. Okay, so for this case, again, let me ask you, what is the maximum shear stress which occurred on the maximum circle, which the two circles overlap here? So this is a maximum shear stress. The maximum shear stress occurred not in the in-plane, actually occurred either in this or in this. So the maximum shear stress is occurred in the out of plane. Okay, so that is the kind of the major concept here. And again, this section is very straightforward, and this is actually the very particular the examples of the stress analysis. We simply kind of dig out this the pressure vessel for the kind of the summarize what we have learned here. Okay, and again, here the one key thing is you need to pick up what is the difference between the in-plane and then the out-of-plane informations. And for pressure vessels, the maximum shear stress occurred in the out-of-plane.